Hello everyone, I'm Darling Eun and my student ID is MAT2309821. And today my presentation title is going to be How Compactness Build Up on Set. And let's begin. Okay, so before studying this study of the compactness, let's recall some concept from the MA1. So actually we need to know what is compactness and why we must study compactness. So, what is compactness? Actually, just say in a humanized way. So, let's start with my barrier head. You can see my barrier head here, right? Okay, so imagine that this is a barrier head and many circles inside this barrier head, and it's got finitely many circles. So actually, every circle got at least one point. So we call that this barrier head is compact. Okay, so why we must study compactness? So you all can see here why we must study compactness. Actually, compactness is an extension of the theorem, extreme value theorem, and the Hero-Borel theorem. So actually, it's also important bridge to the MA2 concept and real analysis. Now move on to the next. So just now, I already mentioned about the extreme value theorem. So extreme value theorem mentioned that the maximum value of function is maximum of the set of f with domain D, and where the minimum value is the minimum of the set function of domain D. So a maximum value or minimum value of a function is called an extreme value of the function. So let's start with the example with the graph that draw below. Okay, so you can see that we got fx graph and gs graph. We can see that the fx graph got minimum value 2 and maximum value 4. But gs has minimum value 2, but it does not have a maximum value. So we can see that fx is closed and bounded and it definitely compact, but gx is closed but not bounded, so it's definitely not compact. So this is the what extreme value mean. So before start with the definition of compact sets, we start with their subcomponent of the definition, which is open covering and subcover. So we say that S be a subset of Rn and let A be collection of open set in Rn indexed by set J. So we say that the A is an open covering of S provided that S in union set of U indexed by alpha and alpha in set J. So we can say that open covering is already guaranteed that have many open covering in the set S, but it doesn't guarantee that S is compact. So it is a kickstart of the compact sets. And then for the subcover, it's a very easy way to understand. So subcover is a finite subcover that contain only finitely many elements in S. So you can understand as a finite collection of the open covering. So let's move on to the compact sets. So in an official way, we say that compact set is provided that every open covering of S has a finite subcover. So if A is an open covering of S, then there exists alpha 1 to alpha k in J such that S in union set of U alpha J and the J is from 1 to k. So you can see that the S is a finite set. Okay. So how we understand this compact set? Let's move on to the motivation and a visual way to understand this definition. So we can see that here have a compact set Rn and we cover it by many open balls. So same with here is a barrier head and we have many open balls on it. Okay, so actually how is going on that infinitely many open balls cover this sets? Well, it is unnecessary because we already overdoing it. We still can use the definition to solve this infinitely complexity structure. Okay, so let's start with the theorem with every finite subset S in Rn is compact and how is apply the definition of compact set in this theorem. So let's demonstrate and just like pick out the structure of the finite subset. So let S in Rn be a finite set, and it implies that we can write that X equals to many vector X, and it has finite countable vectors, which is for some positive integer m's. So obviously, we can let A be an open cover of S, and then each U alpha is an open set in Rn, and by definition, we can say that S in union set for U alpha, but haven't guaranteed that it is compact by covered by K. So now, this is our goal. We want to show that there exists a finite subcollision in A such that S in union set of union alpha and J is 1 to K. So since S is an open cover of S, so we can say that each point vector xj in S must be in at least one open set in the collision. So for each j from 1 to m, there exists some index alpha j such that vector sj inside U alpha set. So you say that this statement is complex, right? So also start with a barrier head understanding. Can see my simple barrier head, and so we just cover in some finite open set here, and then every open set we got at least a point sj in it. So this is the from the definition of the open covering and subcover. So therefore we have the following S in vector x1 to xm, and it also in union m, union n, and union subset of U alpha j. So you can see that actually we follow for the vector set, we already find out that they got union set from 1 to m, and then it's finally you can so this show that it is finally collision U alpha 1 to U alpha n, and it is a subcover of A that still continue covers S. So now we already have our conclusion and reach our goals. So since every open cover of a finite set S has a finite subcover, so we can conclude that any finite set is compact. So actually, now let's have a conclusion here. So we know that compactness is a foundation concept of the connect the real analysis with topology, and it guarantees that the existence of extreme value theorem and infinite structure that help us to ensure the function is behave nicely. So by seeing this definition, we can see that actually any finite subset or closed set, it always compact. So thank you very much for your attention.